I want to thank Jared for the opportunity to be here and to talk about this specific data set. Who's actually worked with MNIST? All right, cool, very good. And if you go to Wikipedia, you can kind of find out all about it, right? You go down way in the footnotes with an asterisk, and you might be able to trace down the kind of information I'm going to tell you today, which is how did this data set even come about? And in telling the story, I hope you get a feel for just how costly creating data sets are. All right, so rewind the tape. So I started in this in 1986. Roll back to the late 80s. What do we have going on at that point in time? Improvements in computation and algorithms. And there's rapid advancement in pattern recognition technologies. This is driving signal processing and image processing. And a key approach that's just caught fire is this thing called a multi-layer perceptron, an MLP, also known as a neural network. Does that sound familiar today? It really does, doesn't it? It's kind of eerie. Now, at that time, this wasn't lost on the U.S. government. The Department of Defense was investing a ton of money and resources into this automated target recognition. But on the civilian side, the Bureau of Census, there was a shout out earlier to that, was great. The Postal Service, and yes, the IRS. They're all looking at how to use handwriting to automate things like reading zip codes so we can get the mail to its proper destination faster. All right, so back in the late 80s, these are the type of neural networks that we were dealing with. They often had one hidden layer. So you got this input layer of your data, you got the output layer of your activation answers. In the middle, you do this combinatorial, nonlinear feed forward and get some sort of prediction. We did a lot of work on not feeding the actual raw data into this network at the input layer. We would do classical numerical methods to create feature vectors that then we would put in to do the machine learning. All right, and oh, by the way, around 1989 or so, Jan LeCun showed up at one of the zip code conferences and said, hey, I've added a fourth layer to the bottom. It's a convolutional layer, and it'll take the raw pixels in and start to do something with it. 1989. So fast forward about 2010, AlexNet comes out, and oh my gosh, we've discovered convolutional neural nets. Well, not necessarily, but you can see that something's gone on here, right? Now, these last three layers, they're pretty much the same technology in the prior slide. But dealing with the raw information in pixels to self-derive image features, that's what's all going on in this deep network. All right, so that just gives you an idea. There's a lot that isn't new, and there's some things that are new. And what's really driving this is more about the data and the computational capacity that we have today. So, why NIST? Okay, so back then, we had this key question: what is the accuracy of hand-printed character recognition? Vendors were selling this to the government. They were running their own benchmarks on their own data using their own metrics. So, how do you know which numbers to trust? And that's where NIST comes in. We help bring objective measurement to technology and emerging technology. So, what do you need to do some sort of a benchmark? You need some sort of calibrated instrument, calibrated artifact, in this case, ground truth data, right? And so that's why this character data set actually came into existence. Real quick in my story, I'd like to talk to you about the timeline. It starts in 1990 with the release of something called Special Database 1. We go out to 1988. Oh, but I thought MNIST was new. No, 1998. MNIST is introduced, and there's all this NIST work that got us there. So I'd like to talk to you a little bit about that. And then, oh, by the way, there's this data point out here real recent called EMNIST for extended, and we'll get there at the end. All right, so the MNIST data set is born through a carefully designed data collection using this type of handwriting sample form. In the end, there's about 100 templates of this form in the original data set. And it was carefully designed. You can see the digits 0 through 9 written out 3 times in order, but then you get this set of variable length fields with a balanced but randomized distribution of those digits. That handled collocation effects and things like that. There's a field down here of lowercase alphabet and the uppercase alphabet. And for some free-form text, which was just kind of pushing everything in the day, we had people write out by hand, again, ask them to print the preamble to the US Constitution. Now, quick story. We sent out thousands of these forms through business return envelopes. They come back to NIST. We start getting 10s, 20s, hundreds. We're like, oh my gosh, we got to open all these envelopes, right? So we borrow a letter opener, an automated letter opener from our mailroom, and a very overly eager technician grabs a stack of these envelopes and goes, okay. They blow open the first envelope. Those forms were bifolded, put into the envelope. So not only did it rip off the end of the envelope, it also severed the forms in two. So anyway, always be careful. And don't entrust your valuable data to inexperienced people. This thing's got a delay that I'm not used to. Come on, there we go. All right, so 1990, we got these, we ended up receiving back 2,100 of these completed forms. They were filled out by census employees. They were field data takers all across the United States. So we had handwriting representation samples across the lower 48 anyway. This data set was distributed on something, do you know what that is? A compact disk read-only memory, right? CD-ROM, right? So this was new technology in the day to put that data out. We could get, what, a gigabyte of data on there or something. So the forms were on there, the full scanned images, and also the cropped out fields of the handwriting. We scanned this in at 300 pixels per inch, and we did it in bi-level, black and white. And just to get to this point, you know, we had to do that data collection design. We then had to do the form scanning. We had to determine an image format and compression because images, they would fill up capacity of disk in that day very quickly. We had to create something called form registration so we could look at the image, find the boxes on the form to find the characters in the boxes, and then do this field isolation. So that was 1990. Then a couple years go by and we're still working really, really hard, and we released Special Database 3. This is a collection of that labeled, segmented and labeled characters that were on all those handwriting forms. And now we had this collection of individual character images of digits lowercase. Each character centered in a 128 by 128 pixel image. To get to this point, the milestones needed were, well, we wrote a character recognizer. So we used a lot of blob coloring, component analysis, and then we had to reconstruct things like when the top of a 5 that's not detached or not attached has to be put back together. So a lot of work in character segmentation. And then before we could send this out, we needed the labels. We needed the ground truth. Well, we were pretty clever about how we designed the form. Remember, on top of the form, we told the writer what to write. Well, maybe they didn't write what we asked them to write. And then you add automatic character segmentation to the whole bit, you now have error. And so we had to human adjudicate all those characters. So here's a quick story. How did we do that, right? We have 100,000, couple 100,000 of these characters. Well, we had a lab technician, didn't have a grad student, sorry. So we had a lab technician who was prone to wander and become distracted and was put under a performance improvement plan of the government. And he had the wonderful measured task to sit in a very cold machine room on a Sun Microsystem display. And what we did is we created a thumbnail montage of 1,024 character images of the same class. All the zeros at once, all the ones at once. And the visual aspects of our human brains, you can sit there and go, oh my gosh, that is not a zero, right? And so you just pluck them out, you could reassign it, and we could comb the data that way. Anyway, we won't talk about the guy's performance plan review. Okay, so 1992, we used that data to run a test. Remember, NIST, objective measurements, let's figure out what the accuracy is for the benefit of the government to run procurements, know how to put in our RFPs the proper error rate requirements and things like that. We also processed another 500 forms of characters in order to do a blind sequestered test set called SD27. That was filled out by some students. And then fast forward to 1995, we repeated this whole process and scaled it up. And my colleague Patrick Grother gets a lot of credit to get us to this milestone. And we have something called Special Database 19. These special databases were put out by NIST in the public domain, free to be used. We didn't put any traceability on it. We knew when people ordered CDs, but you could put CD data up and share it. And we didn't have any protocols on how to use the data. But in the end, we had over 814,000 segmented labeled characters. And to get to this place, we also introduced, remember that preamble paragraph at the bottom? I wrote code that could then take the segmentation in further reading order, use a dictionary to actually clean up the classification with a neural network classifier. And so that is the Special Database 19 that Jan LeCun picked up for MNIST. This database, this data set is available today. Now, all that technology, in order to create this, I put together a package called HSF, Handwriting Sample Form System, SIS, HSF SIS. And this package, it's written in C, so you can probably get it. I'm sorry, it's not in R, but you can get it. You could probably port the code with some work to the modern compiler. But in there is form registration, field isolation, form removal, because we would get the characters and we would segment them out of the boxes, but a lot of times the characters overlapped with the box information itself. How do you remove and clean that up? All that's in there. Neural network-based classification. That classifier code actually contains approaches that are being used extensively still today with the deep learning. And then fast forward from 95 to 98, when MNIST actually is first introduced. Out of all those characters, Jan LeCun, Karina Cortez, and Chris Burgess, they carved out 70,000 of the hand-printed digits. Balanced sets, 50,000 or 60,000 for training, 10,000 for testing. But remember, I said it was bi-level, black and white image originally. MNIST is in gray. Well, that's not real gray, all right? It's a pseudo-gray created through a bicubic interpolation of the binary images and scaling them down to 28 by 28, okay? And so that is MNIST. And now there's something called eMNIST. Oh, and also that's why NIST is even in the name. So extended MNIST. So SD19, 100,000 characters. Only 70,000 were actually put in the MNIST benchmark, particularly with the advent of deep learning, convolutional neural nets at scale. The error rates, as many of you know, are very, very low now on that MNIST benchmark. And it really is time to raise the bar. We're just not seeing enough error. We're not pushing the algorithms enough to really be comparatively useful. So let's see. Gregory Cohen, Saeed Afshar, Jonathan Tapson, and Andre Van Schaik, they get credit for going back to the SD19 and kind of carving out some new sets. You'll see at the bottom of this table the MNIST set preserved for backward reference and compatibility. But if you go 3 lines up to digits, there's a new reference set out there that has a total of 280,000, so that the community can then retrain and start to also generate benchmark accuracy error rates and compare each other to this. All right. I think I blew right through this. So what I'd like to leave you with is some lessons learned. And I'll be around after the break to talk about any of this. First thing, producing high quality, ground truth labeled data sets is costly. How many of you have done labeling of data and created data sets to run your R experimentation? Yeah, it's just a pain in the butt. But there are things that can help. And as you saw demonstrated here, starting out with a careful data collection design can be very helpful. It can save you a lot down the road. Developing a robust tool set in the domain that you're working in so that you can use automated techniques to do labeling, first pass at labeling, and then use human adjudication through visualization or some other secondary means in order to try to clean this up. We were able to estimate that through our validation or authentication adjudication process, we got these labeled characters at that scale down to less than 1 error in 1,000. Then another thing I'd like to leave you with is hang in there. This is what, 2018, fiscal year 2019 if you're a Fed. So we're talking about this stuff was, 1980, late 80s, early 90s. Hang in there, because you never know what's going to stick. My career took me off into pattern recognition and biometrics, fingerprint, face, iris recognition, things like that. I had no idea there was a community that was swelling around some of this SD19 data. NIST found out very late. In fact, where we saw the use of SD19 in the early 2000s was, I am not a bot, where you have to go in and validate that you're really someone. The characters they show, companies realized they could get handprint data for free. so that helped feed that for a while. So hang in there, and I can say that the odds of having something stick increases when your work, in this case data and source code, is made public. All right? And then the last thing I'd like to say is pay it forward, because what goes around comes around. And I know I'm preaching to the choir here because I think this is definitely the spirit of this community. So Jared, thank you so much. It's really the first time that I know of that the real full story of MNIST has actually been told. Thanks for listening. You've been the guinea pigs or the unfortunate first-time listeners. But again, I'll be around at the break. Thank you.